Anyways, marvelous, absolutely marvelous to be here, and I really am quite. I'm honored actually to be at McGill. This is to be one of the best universities in the world. It really is. It is rather groovy, as we say. One little side note: I applied to the Faculty of Music here at McGill in 1983, and I was rejected. So here I am now. I just had to say that. It was good. I ended up getting my music degree at Western, my undergrad degree in music theory. The reason I properly got rejected, I am the world's worst flute player. I mean, I play the E-flat concert radio really well, but yeah, seriously, my flute playing was just awful. But I really love the music theory, which sort of imbues my worldview in MIR. Personally, I came to MIR because of my crappy flute playing, to tell you the truth. We had to play our fourth-year jury, which I hadn't practiced for, obviously. And there was one piece, there was a Bach piece, I think it was actually BWV 1033. Now I know this, but I couldn't find it. All right? Seriously, this is one piece I heard played at someone else's recital. I said, I could play that one and pass. And I went, I'm flipping through all the BWV, and I just cannot find it. So there's got to be a better way. And if anyone ever tried to look for music just by going to the card catalog, like, good luck, right? It's just the most useless thing. And so this was my inspiration. It's like, could we search by notes or whatever and patterns? So that was my inspiration back in 1988. And I never did pass my jury, by the way. I found a piece of music, but I couldn't play it. It was too hard. So then I drove taxi for 4 years. After graduating with my undergrad degree in music theory, I was an independent taxi executive in beautiful London, Ontario. And while driving taxi, I met a professor of the library school, Dr. Bernd Frohman at the bar. We used to frequent Chaucer's. And I used to drive him home. After the bar? Well, this is how it works. So in the taxi industry, this is actually kind of meaningful. In the taxi industry, things get slow around 11 o'clock. Between 11 and around 12:30, because people have already gotten to the bar that they're going to get drunk at. So I always took a break then and go into Chaucer's, which would sell me a cup of coffee and let me use their bathrooms. They had really clean bathrooms. Then, right around midnight, Professor Fromm would always go home because he didn't want to catch the rush. So I just give him a free ride home. This happened like week after week after week. And so we got talking. We became pretty good friends. He ended up being the dean eventually at the library school at Western. But he had the foresight to say, you have this information, you have this interest in things music, and there's always openings for any kind of work on the arts in the library science world. Why don't you come and I'll get you into library school? And more or less he did, and the rest is history. So I did my master's in library science at UWO from after I finished driving cab, so 92 to 93. Then I got invited to do my PhD from 93 to 99. And that's pretty much my sort of academic history there. Came down to the University of Illinois in 1998, ABD, and been there ever since. Okay, so in the talk we're going to give today, it's a mishmash of kind of all the bits and pieces I've been collecting up over the years and forming different modules of things. And some of the key collaborators in this current work are Professor David DeRoer, who's now at the Oxford E-Research Center, and this speaks to the theme of today's talk about e-science and e-musicology. He's a really, really interesting gentleman, very big in the linked data world. Anyone here know anything about linked data? Hands? It's kind of, okay. So it's one of these things that you're gonna have to know. You might not know now, but it's getting bigger, and it's something like gravity. It's gonna come and bite you at some point. Yeah, it's hard to avoid, but there is a lot of hand waving around it that you should, it's understandable if you're not quite attuned to it. And of course, then we got our hero, Professor Fujinaga, here at McGill University, who needs no further introduction. So today's talk is going to involve a whole bunch of work that we've been doing in all these different kind of projects. As we were saying earlier, pre-lecture tonight, it's really hard to keep track of all the acronyms and stuff. And once you get involved, they become the shortest way of describing very complex relationships. So I'm going to try and give you a sense of some of the acronyms that are going to be flying by. And before I get there, I do want to sort of talk about today's title. And today's title is what I am doing, what Itch and I are doing, is it e-musicology? That is, are we actually getting into musicology using electronic tools, or are we still just sort of doing e-science, which is sort of broadly defined? I actually have an answer at the very last slide. There is an answer to this. But to give you a sense of what I mean by e-science, e-science is a very big thing right now in the technology world. You know how computer scientists are always looking for something to do because, you know, the last thing's solved. So e-science and big data is sort of the grooviest new area in which funding bodies are really paying a lot of attention. And the idea of e-science is essentially the construction of scientific work experiments in an electronic environment from beginning to end in the entire research process mediated through an electronic environment. So there's e-chemistry now, e-astronomy and the like. Essentially, you start at the very beginning. You construct an experiment or maybe a modeling of molecules, you say. So you have an environment where you do that. Then you write programs to actually do the modeling. You gather data, you build data, you run your experiment. All this stuff gets recorded while it's running. You get outputs, right? Then you get analyses of these outputs. All this stuff continues to accumulate and accrete, and then essentially you package that all up as part of a publication. So this is one of the new paradigms in the e-science world, is that even your experiment is part of the publication. Your intermediate results are part of the publication. Your outputs are part of the publication. And then, because you now have some algorithms, you have some results, you have some data, all this, that can be reused. Right? It should be available for reuse by students, by other researchers. So they can just plug in and say, hey, I want to take that data set that was created and this algorithm taken by someone else, and off we go. I want to replicate or now extend. This is really big in the world of the funding agencies, because they are getting a little tired of spending millions of dollars generating this data only to have it rot the second that the grant money goes away. That is not being reused by students, not being reused by others. Sensor data is another area in which e-science is playing a big role. I don't know if you know, like the size of the data sets are being generated by all these environmental sensors, like terabytes a minute, all streaming into various spots that needs analysis. All the climate data, for example, right? That has to be managed and managed, used, and then given access for others to manage and use, and so on. So this is a whole paradigm. Big data, e-science, data curation, it's all of a piece. And so that's the world in which was our inspiration for the work that we're working in. And that's one reason why we're working with Dr. David Dorr. Okay, so that's the framework for e-science. Okay, so here we are, and here's some acronyms. Immersal, that's the little lab that is about the size of this piano. Back at the Graduate School of Library and Information Science at the University of Illinois at Urbana-Champaign. The International Music Information Retrieval Systems Evaluation Laboratory. That's where I do my work. That's my locus, where I do all my studies. Related at the University of Illinois is this monster, the National Center for Supercomputing Applications. This is funded as part of the original information highway grants in the late 90s. Al Gore, when he did invent the internet, that's Al Gore's money founded that place. It's famous now for inventing the most common web browser and the most common web server, the Mozilla Netscape stuff. And it was famous for in the middle of building the largest supercomputer in the world until IBM pulled out. So they built the building, and then IBM pulled out. So we have a big supercomputing empty building called Blue Waters, but I think now Cray is going to come and save that. So very big, large-scale supercomputing applications. As part of NCSA, there's a subunit called the Institute for Computing, Humanities, Arts, and Social Sciences. It's sort of an outreach arm of NCSA. It's sort of the friendly phase, bring in the humanities folks, bring in the arts folks to actually do something on the big iron. That's sort of their mandate. Okay, and we've done some work with them. So ISMIR has variously changed over the years. It is the International Symposium or Conference or Society on or for Music Information Retrieval. And I aptly named Symposium. I needed international because I wanted people from all over the world to play in ISMIR. But I wanted Symposium because Symposium, does anyone know what Symposium really means? It means drinking party, right? If its Greek root means drinking party. And I love symposia. So that's why that thing stuck. And then finally we became a society. And actually Itch helped us do all the incorporating stuff. And George Zenitakis is sitting in the audience, is an officer with ISMIR. Okay, this is going to come up. This has also been part of our inspiration for a lot of the work. I run a thing called the Music Information Retrieval Evaluation Exchange. Think of it as a cook-off for music retrieval eggheads. We'll come back to it. I'll explain it in more detail later. But MIREX is important. Out of Mirex and all of this came the Networked Environment for Music Analysis. This was our big joint grant that Itch and I and David Deror and others worked on, and a lot of the results we're talking about today come from the NEMA project. Within the NEMA project, we borrowed some tools from another group at NCSA, and that project was called CIRMMT, or the Software Environment for the Advancement of Scholarly Research, another Mellon-funded grant, building tools to help run the big iron in a friendly way. And one of their tools, the project generated this tool here called Meander. Meander is actually not an acronym, but what it is a flow management system, which is really big in this e-science world. And I have some examples, and it means flow in Catalan. The chief programmer was from Barcelona, so that's why that's that. And then finally, one of the outputs of all of this nonsense is the project that we're just wrapping up now with Itch and Dr. Deror, the structural analysis of large amounts of music information, or SALAMI, because acronyms just don't get any better. I love acronyms. Though, got to pick your acronyms more cleverly next time. It's how every project needs an acronym and a memorable logo. I do not recommend SALAMI for any future project. It's really hard to come up with a logo that won't get you arrested. It's just there's no internet representation that you can sort of do. So we gave up on it. We just sort of. Yeah, so SALAMI, not the best for logos. Okay, so what is music information retrieval? I realize we have a kind of a mixed audience here today. I see some old faces, some people that have been actually very active from the beginning in the MIR world, and hi guys. And some new music folks. I realize that the music school has a wide variety of interests and intellectual background. So I'm just going to very briefly give you my whirlwind tour of what is music information retrieval from my viewpoint. So it actually started in the 1960s, back in the days when big iron became available on campuses. And a lot of interested folks saw the opportunity to maybe do some what I today call symbolic searches across collections of music. So they spent a lot of time thinking about ways of encoding the music. There was work about Palestrina and motets, and then they tried it. They kept working at it, and it kind of died, right? And the reason it kind of died is that the representation problem became a huge issue. It almost became insoluble. They spent more time arguing or just trying to figure out how to convert scores into some kind of format that the computer could deal with in the day. And it just sort of faded. It was way too much work. Then what happened later on, a bunch of things happened. Computing power became more ubiquitous. Audio files became realistic and the ability to play them. Hard drives became bigger. And we got into the world where people had images, had viewpoints on what Google or Yahoo or then Alta Vista could actually do. So they had a mental model of what a search engine actually could happen in a large scale, right? So this re-inspired people that had a music interest. Oh, we got MP3s, we got Google. Why can't we sort of do Google for MP3s? And this is where in this sort of age, this is where sort of the modern, the latter-day interest in the late 1990s of MIR came about. So we had a preliminary meeting in 1999, and we had our very first ISMER meeting in Plymouth, Massachusetts in 2000. And actually, George Xenotakis was there when he was a student. Okay, so how am I going to define music information retrieval? Here's my broader definition, sort of my pie-in-the-sky definition. So music information retrieval is the process of searching for and finding music objects, and that's a weasel, I'm being weaselly there, or parts of music objects via a query framed musically. This is one thing we want to get at, is that we're dealing with music as music and or in musical terms. So musical objects, this is where I'm sort of agnostic about what the actual music object might be. It could be a score, could be a part of a score, and recordings and so on. Lately, I'm going to back up. When I started, this is the realm, this thing working? I was working in this realm coming from my music theory background. This is the realm where most of the world's working in now. It's astounding, sort of the flip. The amount of work that electrical engineers have done in dealing with audio is amazing. It's just earth-shattering, actually. Paradigm shifting. So, and of course, musically framed query. So you can, someone could sing, very big or hum, very big in karaoke. The Asians are really big into this line of research. Keyboard, as in keyboard like this, MIDI keyboard, notation or MIDI files or sound file, query by example, and so on. And of course, we have the whole, music is a whole art form, a whole language of its own that has certain nuances and stuff, and then we have to reflect that properly. So what makes MIR so tricky, and this is sort of me being clever for my PhD work. So music is multifaceted, has many different components. It's multimodal, exists in sound, in scores, images, performances. Multi-representational, even within, let's say, I have a cute slide about the number of different ways you can represent music. Multi-experiential, this is where we get the humans into it, how one person experiences music. And context of experience that music influences what would be a proper query or a proper relevant result, and so on. And of course, multicultural. We do have a problem in MIR where we tend to focus on collections that we have at hand. So they tend to be Western pop music, right, and a little bit of Western classical. And that's pretty much the gamut of research in MIR. And it's quite a problem because all the tools are getting biased towards those kinds of collections. So we're really not doing well on the multicultural or more complex musics like jazz and so on. So here we go. At someday, not now, not tomorrow, but later, we're going to have to deal with music in all its glorious ugliness. I don't know if you're going to have to help me with this. This is an old slide. I think this is Korean, to be read up and down. There's a piano roll, of course. There's a MIDI representation piano roll. That is a piece of music right there. It's a max patch, I think. Is that what it is? I can't see it right anymore. Yeah. And various other fingerings and like that were just sort of collected at random. But at some point, we're going to have to deal with all this. At this point, we're bailing. This is too hard. Okay, so as I mentioned, one thing that really surprised me over the years, when I started in this realm, I came from an information retrieval background from my new discipline of library science, where everything was represented as a string of text, of symbol characters, and you did all kinds of crazy things to get the computer to search through those strings of characters. I had no idea how far audio, the idea of searching through audio was just like, yeah, sure, that's Star Trek, that ain't going to happen. My viewpoint has absolutely flipped like 180 degrees. Music information retrieval now is predominantly run by electrical engineers or computer scientists with very strong digital signal processing backgrounds. And this is sort of biased. This is now a theme in our talk. Their techniques, their abilities do shape what we see as legitimate kind of research in the MIR world. I think it's a bit narrowing. I think time has come where we have to get out of this and move on and do things more broadly. Get back into the music. But I have to say, over the last 10 years, the amount of progress they've made by dealing with audio as audio has been astounding. So we have a lot of refugees from the EE speech world, phones. All the efforts that went into sound and phone, cell phone stuff, all those cool algorithms, essentially, hey, we got all these cool algorithms over here, let's throw it at music and just see what happens. And you know what, it was sort of some of it really works. It's really quite astounding. So it's a great place to start. One thing that, I don't know if you know much about the world famous fast Fourier transform, where we convert the sound waves into its constituent sine waves. And then you analyze that and all kinds of these magical spectral manipulations. Who here has heard of a Mel-frequency Kepstrel coefficient? Yeah, that's the usual suspects. Hello, usual suspects. Who has not heard of them? Okay, here's where I'm not an electrical engineer, but I drink with them when I go to conferences. There's a whole bunch of these spectral manipulations that change the underlying parameters of a spectrum. All of us here pretty much at a music school can know what a spectrum is. And each have different properties. And the one thing that these EE folks have, they love anagrams of the word spectrum and spectral. So anytime they do one of these mathematical variations on the spectrum, they give it a name that's an anagram. So when I said Kepstrel, can anyone do the jumble word? It's spectral, right? So all that really means is that they take the spectrum and they do a transformation on it, and it yields some other kind of view of that spectrum. And so they do this all the time with these different kinds of things. It turns out this one was used a lot. It has to do with speech. And it was our hero, Beth Logan, back in 2000 actually. She worked at HP in the speech lab. She threw MSCCs against the audio collection, and it really worked. It's another way of analyzing the audio, and you can search through it. And so it's like everyone uses it. There's actually theoretical reasons why it shouldn't work, but it does, and so people use it, right? And then, so we have the speech. So we have this sort of speech stuff. Then we have our friends in computer science. They bring us the machine learning, right? So it's the machine learning side that we get from the computer science folks. And essentially pick any kind of machine learning technique. They throw the kitchen sink at it, and we've tried it, and we're working on it. So it's a combination of cool stuff from EE and cool stuff from machine learning. That's the modern instantiation of what's going on in MIR. So I do note, for all you folks that are like ethnomusicologists and real music theory folks, very little's happening on the symbolic side. And I apologize on behalf of my fellow MIR researchers. It's harder. The tools aren't there. Okay, so indexing, for example. We're not doing much in the way of specific indexing. We are doing some audio stuff. So what kind of queries can we perform? What can we evaluate and improve their techniques? And one thing we haven't spent too much time on and we should get back to is actual usable interfaces, human-computer interaction. So compression is always an issue, though everyone just deals with MP3s because that's what exists in the world, and so on. And audio feature detection. This is a big area. What audio features do we take out of the music audio that actually means anything? You can get feature bloat, hundreds of thousands of different features to look at. A lot of them, some of them might work, some not work. And that's an ongoing, there's no a priori theory that says, you need feature X. And of course, then we get machine learning. So which machine learning algorithms will actually work, and what kind of classification techniques to work on these collections. So here's a classic model. I don't know if you've done much in the way of sort of machine learning and idea. So this is, you start with a data, some music, and then you apply one of those great MSCC analyses kind of things. And what you do is you break your audio into different features, right? Just a feature vector. Maybe in a simplest world, you might have a feature that says how much energy is in the low notes, how much energy is in the medium notes, and how much energy is in the high notes. That's a very simple thing. So we could have, say, low energy, amount of low energy, amount of medium energy, amount of high energy. And then, essentially, could be one slice of or one representation of a piece of music. And you do that for all the music in your collection. And then now you can position these three points in some kind of space. And when they start gathering up, you say, oh, something's happening over here. They're similar. Something's happening over here. There's another group. So this could be classical. This could be rap. Right? And we've literally done those experiments over and over, and it works. There's quite good success in those various kinds of approaches. It's actually kind of fun. It's a great kind of project for undergrads to fool around. So we operate in these different domains, right? We offer in the frequency domain. You can see the pitches going through there, and we also operate in the time domain. So essentially, a lot of the time, we kind of move from the time domain in the raw audios in the time domain into the frequency domain and back forth as we extract features and try to figure things out. Time domain's important because music exists in time. It evolves over time. In early days, we'd tend to take an entire sort of frequency domain and munch it down to an average for an entire 3-minute pop song, it's a good first pass. And for a lot of pop music, who cares? Because nothing happens in 3 minutes anyway. Right? The average is the piece of music. But when you get into classical music or jazz or anything where it actually has some musical, it evolves, right? So that average totally misses the point. So things are happening now. We're moving away from sort of simplistic things and getting back into taking time into account, evolution of musical events over time. So here we go. So we have the notion of different kinds of classifications going on. So we have unsupervised, where we essentially build clusters, right? And of course, supervised, where we had this notion of ground truth. So one of the classic examples that we have a collection of 1,000 pieces of music, and we know the genres, right? So we have maybe 10 rock and roll songs, 10 blues songs ad nauseum, blah, blah, blah. And essentially, we train the computer to say, hey, listen, here are the jazz songs. Listen, here are the blues songs. Then we run the experiment again, take the labels off, and see if the computer can put the labels back on. That's your classic supervised learning train test kind of algorithm. It gets used a lot in MIR. So in 2001, we had Izmir meeting. And we realized that the papers were pretty cool that were getting published, but they were operating on really small sets. Like essentially everyone was writing their papers against their personal CD collections, right? So, you know, I have 5 jazz CDs, so you write a whole scientific paper on how well your algorithm can find 10 songs in your CD. I mean, you could look quicker, right? And probably more accurately than actually run the algorithm, right? So in this report, we had a scaling issue. So we went and got some funding from the Mellon Foundation, National Science Foundation, to see if we could build some collections, real size collections that we could work with. And we had some meetings and this is where this Murex idea comes from. This is our striving to get a bunch of standardized collections, to get big collections or bigger collections so people could try their algorithms against a common data sets. So TREC, that's the world I came from with my library science background, is the Text Retrieval Conference. They've been doing this for years, since about 1991, I think. They get huge text collections from newspaper publishers or database publishers. So they'll get gigabytes of news data for a year, and they'll get people to write up some questions. So how many people were killed in the Lockerbie bombings? Right? And then everyone gets a list of 50 questions. They download the data set or get it on DVDs. They build a search engine, and essentially they mail back, okay, for question number 1, here are my top 10 answers. For question number 2, here's my top 10 answers. And they get retired spooks, literally, retired CIA agents to go through and read the answers and see whether, yes, that was a good answer, or no, that's a bad answer. So a hit or a not hit, and then they come back, have a conference, and they find out which algorithm works best. And Google's played in this. They do this every year. It's a great model. We can't do this with music. The problem is we can't ship the music around. We have the hardest time getting anyone to give us real music to play with. So we've come up with some clever ideas. And one of our clever ideas that we have is what's known, instead of a data to algorithm model, which is what happens in TREC, where people deliver the DVDs to their labs, we have the labs bring their algorithms to our lab in Illinois, and we run the algorithms against our data. It's called non-consumptive, is another word for it, and it's gotten us around the copyright rules in a big way. So security, we want security for the music materials because we'd like to get more collections. However, then we have this conflicting thing. We want accessibility for international, domestic, and researchers, so on campus, off campus, around the world. And of course, one thing, when you do all this audio processing, it generates tons and tons of intermittent results, and it burns CPUs like no tomorrow. A lot of it's really intensive, so we got to make sure we have enough horsepower to run this stuff. So here's our model. Basically, we created sort of a closed little system. This is kind of an oversimplification. Then we have thin connections where people essentially send us their algorithms to run. So we began Murex in 2005. Tasks are defined by community debate. Data sets are collected or donated. We got most of our really good collections from retired PhD students, because only PhD students are insane enough to sit down and create ground truth. Ground truth is the most painful stuff in the world to do, and it's only when you're motivated to get your PhD that someone will actually sit down and mark at the 20 millisecond level whether a music event's happening in about 4 hours of audio, or actually note the pitches in a live performance. So we tend to get them from retired PhD students, God bless them, and then people submit the code to us. It never works. So we spend hours and hours trying to get to work on our system. So we lot of labor, and then we meet at Izmir as a half-day event at the conference. So part of this is what inspired Nima to get going. Yeah. So anyway, we've run 1,407 algorithms. Yeah, it's quite a few. I'm really proud of this, actually. It's sort of yay, go me. Yeah, seriously. So a run is essentially one algorithm, one data set, one set of answers. That's what we call a run. So we run 1,407 of them. So it's quite a few. Here are the kind of tasks. These are things. A lot of this is defined on whether we have a data set or not. Right? It's not. We're sort of lagging behind the curve a bit. So we got score following. That's a good one. Symbolic genre classification, which actually run out of here. Key finding, symbolic similarity. Query by tapping, which I hate. Query by summing, which singing I also hate, but they're very big in Asia. MS0, that's a really hard one. Essentially, the test that we have is a Beethoven quintet. Essentially, can the computer parse out all the parts in real time? Tempo extraction, audio tag. becoming very big as people start tagging music in spaces like Last.fm. Can we get the computer to behave like a human and put on tags as if a human would have done it, right? Then that's sort of that kind of idea. Drum detection, genre classification, key finding, melody extraction, that's in the mono realm. Mood is another big area right now, and as is music similarity. This is the closest thing that we have to sort of a classic retrieval task. As you can see very quickly, I'm falling behind here, so I'm going to start rushing a bit more. You can see sort of the popularity relative to how many runs we get. So tag, you can see how many people want to play in the tag realm, because that's a really interesting problem. I really enjoy the tag.
Superscript A?
Oh, that's how many subsets. So yeah, so if boom, 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 so that means it's probably we have two audio tag collections. Actually, we do. We have the Tagatune collection, and we have the other one from. Yeah, exactly. That's what that means. And you can see some more run distributions there. So anyway, Mellon Foundation has been really good to us, giving us millions of dollars to run this. And I finally got called into the office last year and said, "That's it, you're done." So they gave me $300,000 in parting gift money. The basic premise is that over the next 2 years, I have to find a way to fund Mirax without asking Mellon, and that's what the Mirax Next Generation project's all about. And it's kind of interesting, and I'm up for the challenge. And the world's changed since we got started. There are new things happening in the MIR world, and this now starts again in this big science, big data realm that we're not operating in quite yet. So the million song data set, which I can't speak to as well as I should, but that is what it says. They have a song, they have a collection of features, of 1 million songs that were put together by, is it Columbia and Equinest? There's a sort of, as a starting point, right? So 1 million songs, that's a big collection. But it's not the songs themselves. They have a nice, clever workaround again about not being a Napster, not being a publisher. It's features, right? It's the features extracted from 1 million songs that people have access to. But you know what? It's a great start. So we have to work in the world of the 1 million song data set. There's Magnetagatu and other collections going on, and of course Salami. So we have new data to fool around with. And of course there's some other evaluation campaigns going on there. There's Music Clef is a project out of the EU, and K-Mirax is a project out of the Korean Electronic Technology Institute in Seoul. So essentially, what we have to do between now and, actually that should be 13, essentially rebuild Mirax and think of new ways of doing things. Okay, so out of Mirax, and one of the problems we had in Mirax was we tried to automate Mirax. That's what NEMA at the end of the day was all about, automating Mirax because this stuff takes so long to run. And we borrowed some tools from other, actually, NEMA was named by Itch, to tell you the truth. I've forgotten about that. He came up with that, because I came up with the Pan-Galactic Distributed Music Analysis Tools project with no clever name, and then Itch said that was too long. And the acronym is like, doesn't work that well. Yeah. So anyway, so we brought some international partners, UIC, myself, McGill, Itch. Goldsmiths, we had a really strong music technology program. And Queen Mary, very strong in the signal processing at Queen Mary. Southampton, Oxford, that's Dr. Deror, the linked data world. And Waikato, digital library world. And WECA, the machine learning, the University of Waikato, that's David Bainbridge. So again, right, so classification tasks, right, there's a feature extraction component, there's a machine learning stage. Why can't we sort of separate those out and build tools so we can plug and play these different ideas and reuse this stuff, right? So one of our grand framework here is that we're going to take tools that already existed. Some of the stuff actually comes from McGill, the whole JMIR stuff, Corey Mackay's work. My experiment comes from Southampton as another one of these flow things. A lot of these tools, JAudio and the like, and the OMAN, the online on-demand metadata extraction network, is work that comes out of Itch's lab. We're going to put all this stuff together. And the music ontology and Greenstone, which we'll see in a minute. The other one thing, and here's a name that will resonate with some people in the room. People in our community write sort of prototype code. MATLAB is a huge language. It's seriously, the number of submissions we have in MATLAB is huge. There's There's an okay kind of program out there called Marcius. It's Dr. Zenitaka's program, so I'm just being a smartass. It's like probably the #1 used freestanding program in our world. It's open source, and students just love it. And so they write their programs and submit it to us in that. So we need ability to wrap all these various pieces. So that's why we use Java as wrappers, and then run it on the big iron on behalf of people. Here's one of these wrapper programs. Essentially, here's an experiment. Bring in some music, run your analyses, then build your classification, then test it, and then poop up some answers. That's a very classic kind of flow model that we would run Murex run. Then over time, we moved and got new tools. Essentially, this is the more modern instantiation. Yet another grant, make it different colors. Same principle, yet another one of these flows that runs these experiments. So our goal here with NEMA was essentially to bring pieces together. So maybe an algorithm from for Lab A to build a collection from different spots. So maybe a little bit from the Million Song data set, maybe a little bit from McGill, a little bit from UIUC, right? Bring those together, get some ground truth for some poor PhD student, steal someone's feature extractor, let's say from Lab Rosa at Columbia, right? And then get another set of features from, say, UIUC, get some classifiers from Germany, and then just run a big experiment. And then see what the answers are. And if that works, then that whole thing gets packaged up, it's out there, and someone else can take it and run it against something else. This is our sort of reuse, reduce, recycle kind of idea. Because people spent money building these classifiers. People spent a lot of time building these ground truth sets. That it's all about reuse, and it's like science, right? Replication. One of the ways that we're going to do this, and this is where Dr. Dorr's work comes in, is through this idea of linked data. Resource description framework, this is where you should write a note, and if you ever get a chance to bump into this again, you're going to, as musicologists especially, any place where you're going to interchange with music information, this is going to become more and more important. And it's all this world of what's called linked data. It's these collections of disparate bits of knowledge that have an underlying structure that's what's the word I'm looking for? Compatible with each other, so that you can draw connections across disparate databases. And that's our model that we used to run our system. So basically, after we encapsulate one of our little experiments in one of those flow languages, the Meander, it is actually represented as a bunch of RDF triples called triples. And essentially, it's all the information that recorded all the information about how that experiment was run. And so you can unwind it. If you just load it in again, it has all the places where we got the information and so on. And it's really quite powerful. And this does come from the very much used in the e-science world. Good old linked data. So here's a triple. So essentially, they're just 3 statements, right? So there's Y are a musical artist. So this table Y is a musical artist, right? Depression is Ridiculous is the name of an album. Passive Defiance has a track on this album. And you just make assertions about the world in these sort of triples. Then these graphs get formed. Now we have all kinds of interactions, right? This Ireland information now could be a link to yet another database, right? About information about Ireland, right? So now we can maybe start positing questions. Does the color green affect this band, right? That is a legitimate, that you could construct that query, right? You can actually run that query. And this is where the musicological, music theory potential of these tools exist. It doesn't really exist yet, but the potential's there. And everything's represented as URIs. Even so, we have this is what is this? I don't know which one's which. This is the definition of what the relationship is. That's the definition of music artist, and that's actually the name of the artist, represented as a URI, or Uniform Resource Identifier. Benefits of URIs is that machines can process them and they're unique. That's the best bit about it. So here we are. Here's where we start to make interconnections. Jamendo. Anyone heard of Jamendo? Anyone not heard of Jamendo? So here are the not set. Jamendo is an open source popular music site. There's an artist sort of published there. It's not bad. You should go there. It's medium, right? Sort of coffee house performer level kind of folks. But it's big. It's gigabytes of audio, but it's open source. You're allowed to use it. So it has artist information that actually is formatted so that you could tie into geonames. So whenever they talk about a place, you can then go to the geonames database, which is in a whole different world, a different place, and get information about places. Jamendo has identifiers that can link it into music brains. Music brains then can get you metadata about the song you're looking at, right? Then music brains and dbTune are interconnected, right? Friend to a friend is a great mechanism for identifying people. It's a formalism for identifying people. So now, if we find some information about a person, we can get more information about that person by looking in the friend to a friend database. And this all gets tied in. And no, you can go from music brains to Project Gutenberg. Think about that for a while. Right? And this has been growing and growing and growing over time. It's just, seriously. So this is sort of, every time you see one of these maps, it just gets bigger. Audio Scrobbler, right? This is the home of Last.fm. Now getting Magnatune, another collection getting tied in. BBC is now embracing, and this would be really good for musicologists, BBC is embracing RDF and the music ontology as a formal description of all that's published in broadcast music. Right? So if you can get on top of it, you can now get performance information about some really important composers and performances and histories and stuff like that. So that is kind of important. So here we go, right? This stuff is exploding, right? There's our DBpedia again. Our music stuff's kind of, where to go, kind of in there, and then all around here. And it just keeps going and going and going. Yeah, right? And so on. Okay, I'm gonna skip that. So anyway, pay attention to RDF, pay attention to linked data to get a chance to learn more about it. It's worth knowing about. So basically, we built this monster system called NEMA to put all these pieces together. The executors, the data, the store, the results, the store, the parameters, and so on. Other things that came out of this one's more fun. This is the E6K, the Evaluatron 6000. I love that name. This is where we get humans to listen to pairs of music. So the algorithm would say, this song sounds like this song. And say, okay, algorithm, we're going to put you to the test. We load it into this system, and we get humans to actually say, listen to song A and song B, and then they rate it, whether yes, it is, in a broad category, not similar, similar, or very similar, or give us a score. And we use this as ground truth to check the success of our various algorithms. The NEMA DOA interface is the other thing that we built. So this is where we take someone's algorithm, and we load it into here. So now it's encapsulated. And so we can call it again, change a parameter, call a data set, fix the two together, hit run, and it runs, and it goes into the database, and we get answers back, right? And then I can do it again. I can say, okay, I ran that experiment, bring that up again. Now I want another set, plug it in, wrap it up, press a button, gets all archived, right? It's all this kind of e-science, reuse, reduce, recycle kind of system. One thing I don't like about it, it's as constructed now, of course, we're out of money. The interface itself is very computer science oriented. This is not user friendly unless you're a Java geek, right? So that was one of my biggest disappointments about the project, is that we never got to that more user friendly interface. One thing it did do for us, when we run 1,400 algorithms over the course of time, we had to put the results in by hand. It's now printed out all automatically. With all kinds of really cool reports. And this is that classic kind of e-science output. You know, this is the data set that was used. It was run on this day, right? Here are the people that are involved, contacted. This is all done automatically. So I love that, and I think we did a really good job on that. We also built some visualization tools so people can get a better idea of how these things are working. So we have this idea of ground truth, and then we have the idea of what the other algorithms pooped out as answers. So this is onset. So you can see that the variance between ground truth and between the participants. Melody, you can see here what the actual answer is and which one's which. So ground truth is red, that's the actual melody. And what the algorithm thought it was is in blue. So here, you just by looking at this, you can say there's a thresholding problem. If they turn down the threshold, they probably get much better. They get much better results because they're just being a little bit too filtery at this point. Because when they nail it good. They're just missing it. And false positives. Chord detection is another groovy one. This is getting closer to music. This is where I'm starting to get happier about the MIR world. So this is ground truth with actual chords, and then here's all the different algorithms, their versions of what's going on. And so you can see, we're not fussy about the actual spelling of these things because it's all enharmonic anyway, right? And we get really weird, like D-flat major. Who the hell ever heard of D-flat major? Right? Why? But anyway, so the one thing that's really kind of groovy about this, this guy cheated, OGF. So they're supposed to, onset time is important in the scoring. They just said, screw it. I'm just going to report every 20 milliseconds what I think it is. And still I'm getting a good score because people sometimes they game the metrics. So yeah, so you can game the metric by just not following the rules, pretty much. This is where we get into salami, the structure analysis. This is actually from our salami work. So the bottom here is the ground truth. You can see how things are broken up. We've got a refrain, verse, bridge, and so on. Underneath, we're not all that terribly worried about what these labels are. It could be A, B, B, A. I actually prefer that. And then here's what the algorithms do. And you can see there's actually some really interesting consistencies amongst the algorithms. None of it's totally the same. Okay, so salami. That structure analysis thing was one of our inspirations for salami. Structural analysis for large amounts of music information. This comes out of Indiana. This is a handcrafted tool from the Variations 2 project. This is the teaching tool. This is rounded binary, which everyone in this room should probably know. And so they went through and it's tied in with audio, and I think Professor Erickson actually probably built this. And to show the kids how that stuff works. So our goal was, could we get the computer to do something similar? That was fundamentally our question while we're sitting around in Tokyo drinking way too much sake while Itch was on a sabbatical. Itch worked all the time when he's in Tokyo. Work on a sabbatical. Yeah, so we came up with the idea in February 2009. We presented it to iChas. They gave us 250,000 hours of compute cycles, which we still have. And then, because we had this and we had the idea, we won a Digging into Data Challenge grant with NSF, JISC, and SHRC, which is just wrapping up this year. So here's some other inspirations. Ideally, in the future, we'd like this to happen, or this, or this. This would be kind of groovy. We can get that to do it. And again, I mentioned this twice now. There are references for that, but I've lost the citations. And actually, yeah, we've got to find those. Yeah, thanks. Yeah, good, thank you. I really should get them back on. So that essentially says that. So we claim that a resource of this size empowers musicologists to approach their work in a new and different way. And that's true. And I want to make this really clear. I don't want to supplant what musicology has historically done, music theory historically done. But one thing I can win in kind of give an argument is scale. It is one thing to sort of have analyze all the works of Palestrina and know them inside and out, every last variation and notational nuance. But I challenge any musicologist on the face of the world to have in their head 250,000 hours of music. Right? It just cannot be done. It's like 30 years of music. That's literally 30 years of music that we can analyze now, but on big iron. So I think that's the thing we're being groovy about. We're nowhere near the fine nuance and subtle stuff. But on the big picture and analyzing tons and tons of music, there's something to be said. So this is new. I think this is, and I'd like musicologists to pick up on this. And then you can ask different kinds of questions of the big data. Okay, so this is from one of Itch's slides. We have the signal, and this is where the world is, right down there, the classic kind of breakup. We got the 23,000 hours of recorded music. The student ground truth, which was done here at McGill, the great collection. And then we build it into some linked data sets, and we bring in algorithms from the music retrieval community. And then we run it on supercomputers, and we see what happens. And so the ground truth is generated by hand with clever McGill students, and that's actually was generated here, probably. Where Ashley? Across the road?
It's
across the street? Yeah. That data came here from.
I guess the people could work. We set up a website so people could work wherever they were interested in musical structure.
Yeah. Yeah, so anyway, it's a brilliant resource. It really is. It's changing the way people work in this area. So different layers, uppercase letters indicate large-scale sections and lowercase or small-scale sections, and a fixed vocabulary, which we haven't been fooling around with too much. At this point, we're still working at sort of A, B, B, A kind of ideas, and of course, important instruments. So this is really good data, really important. So there's a classic example. So actually, this is interesting. So on average, it's about 20 minutes per song. So if you have 23,000 hours of music, it's a lot. Yeah, seriously. It's a lot of labor to get this done. And then it was done twice to get agreement between things. So at some point, we are going to need machines to process this because we just can't do it by hand. There we are, 20 minutes, median, majority 15 to 20, and so on. So again, this is all about interlinkages. This is where the linked data idea really plays. We got the signal, we got the analysis, we got the community involved, we got ground truth. It's like a web. Okay, so the Salami project, web accessible collection of structural analysis files. We're still working on that, about 350,000 pieces. Here are some of our collections. So some of them are a bit noisy. We're going to the McGill collection, the stuff we have for Mirax. DRAM is a very interesting musicological collection. What is the Old New World's Records run out of New York? Some interesting Americana. It's mostly Americana. Internet Archives is the biggest collection of Drek ever, but it's groovy. It's like Fish art, Fish concerts and a whole bunch of bootleg. What's the band? Jerry. Yeah, Grateful Dead. Just hours and hours of Grateful. And and some guy standing on a street corner playing like a ukulele really badly. Right? Just anything. Seriously, that's the Internet Archives. They're not fussy, but it's data, and and it's real data. I mean, it's data of music in the world. Right? Not everything comes in nice studio unmixed packages, right? So you got to deal with that. We're not good at that. We're not really good at dealing at music in the wild. So interoperable file formats and the ontology. So that's what we've been working on for people to grab this data and use it again. RDF, again, so one of the things that there's a tool that comes out of Queen Mary, one of our partners, that will eat RDF files. And so you could load in one of these structure files, and that's what this is down here, and you could lay the structure on top of another representation, on top of the audio representation or the spectral representation or the time representation. So it's another layer that we can provide. Okay, so open source and let the software essentially distribute the software. So I'm going to show you a bit on how a lot of these things do this, and then it'll get us to our little demo, and then we're done. Okay, so this is a chromogram. It's essentially, and this is where I need my double engineering friends. Basically, a chromogram is frequency bands based on the chromatic scale. So we just essentially, I don't know which way is which, but just imagine that this will be C, this will be C sharp, and so on all the way up. That's why there's 12 of them, if you can see that. And eventually, how much energy is in that particular band, regardless of octave, right? So how much C sharpness is happening here, how much D-ness, and so on. And you can actually start to see the individual pitches. If you look closely, there's a lot of energy in those. And if you could follow it, that's probably a melody of some sort, right? So that's the notion of chromogram. It's very popular. And it gets you back into the music a bit, because essentially it gets into the melodies and harmonies in a clever kind of way. So what they do, and this is where I think is the grooviest thing ever, where I have nothing but respect for our double E and computer science friends. They take these chromogram information, they take a slice, let's say like once every 50 milliseconds or so, and that's great. And they run this, they do a self-similarity matrix. Essentially, how similar is the song at this point in time to the song at this point in time? And they do it for all the combinations, right? And that's how we get this big-ass matrix. It's symmetrical, so you only need this triangle or this triangle. But the key, where the clever bit comes in, after they crunch this, is that you can start, what you want to start doing is locating diagonals. We know, for example, that the song is the same as itself when x equals y, right? So when the song at x seconds, so let's say x equals 4, the song at 4 seconds is the exact same as the song at y equals 4. It has to be, right? X equals y. It's the exact same thing. And that's why we get this really strong diagonal, because it's exactly the same. It has to be by definition the same. Taking that little bit of information, anytime you see an off diagonal, you see there's something going on there that's similar. Some similarity actions happening there in that domain. So you use other algorithms to try to find these diagonals, and you mark these diagonals. This is going to be where we start to deduce structure. So here, for example, we have a strong diagonal there. And what you do is you project the diagonal at 90 degrees. So you project the diagonal from this point across and from this point down. And what we've just shown is that this section here is the same as this section here. It's a repeat, right? And this is how we start to deduce structure just by using clever computer algorithms. And it really works. It is frightfully cool and groovy. So now, without sort of being a human at all, we've been able to say that this piece here is it repeats there. And that's sort of at the heart of it, right? And we can go on. So basically, this is a real piece of music that's on the website. We have this sort of big section here that's kind of mungly and not very good. Then we get, well, we notice there's a big section here, projects there, projects there. There's our B. Here we have another very strong diagonal, project that down. We get the C and C. We got the B. We got something in the middle that doesn't really match up with much of anything. Boom, we now have an analysis. We have an A, B, C, D, B, back to C. The computer just came up with a structural analysis of this piece of music without a human. And when you listen to it, it's right. And you also see, you can see the eyeball. You get good at eyeballing this stuff. So anyway, so an open source ground truth set, and this is where McGill has done a marvelous job. They're releasing the ground truth set for other people to play with. So a mix of things. So double keyed are the numbers of songs that were done by 2 people, which is good. That's very useful information. Single keyed, and so on across a wide variety of genres. And run some experiments. So we have been running some experiments on the data. Okay, so I'm going to give you some closing thoughts, and then I'm going to get to the very last, show my little demos, and then wrap up. Okay, so right here, one thing I want to stress to everyone is that music music in the computer realm is important, right? And I always get grief whenever I travel. You do music, who cares, and whatever. Well, I don't have to talk to you guys. You guys be fearless, right? Seriously, you don't need any excuses to look at music. It's music, and they can go screw themselves, right? Seriously. So don't be frightened, be bold. One thing I do say, if you have any ideas or anything you'd like to do in sort of this realm, I'm a really big believer, and I'll say this over again, make it a contest. Right? It builds community, it builds esprit de corps. Come up with something where you can bring in other people. Definitely. Come up with some kind of contest to tackle your problem. And here, even I'm going to take more lectures. I'm going to learn more about this. But this linked data stuff is happening. And you could really make it your own and really make it better. Because if you don't, someone else is going to do it. And the music ontology, which is a shame, was written by an electrical engineer. The single unit, the functional unit in the music ontology, as much as I love the person in it, is called the signal. It's not called the music, it's called the signal, because it was written by an electrical engineer. And this is the stuff we have to avoid. The librarians of the world and the musicologists of the world have to get involved and start helping to structure these things, because the computer scientists and the engineers will do it for us and not do it as well. Okay, that's my little spiel. Here we go. Here's something this is where we combine in the NEMA framework some of our tools. This is where we kind of groovy stuff happening. Tool number 1 is Greenstone. This is a digital library program that comes out of the University of Waikato in New Zealand. This is David Bainbridge's work. Very famous in the digital library world. It's now their version 3 of Greenstone. It's open source. They're big on open source there. It's used in the third world. It's used by the UN. And I use it to teach. This is how I teach my digital library classes. So that's tool number 1. Tool number 2 comes out of a combination of work, Dartmouth and Goldsmiths. It's a program called AudioDB. It does audio searching for similarity. We embedded that inside of Greenstone. And then, all wrapped up in that is the salami data. We took all the salami findings that we had, and that's what's inside this digital library. So it's a combination of a digital library tool, the audio search tool, and the salami stuff, all brought together in a groovy new package. And so at this particular point, I'll give you an example of sort of what happens here. Let's go artist, and actually let's go track. Track's probably better. Let's do Michelle. Michelle's always a good one to show sort of the tool. Yeah, sorry, my head away. My big fat pumpkin head, as my wife says. And I should learn how to sort. M-N-O. Michelle, my belle. Okay, so here we go. I don't know if you can. Oops. I didn't want to do that. There we go. Now can I make this a little smaller? Maybe not. Okay, so I'm going to sort of parse this for you. What we have here, if I'm not mistaken, are a bunch of things going on. Here's one of those chromograms, right? Notice just your naked eyeballs with your power of your eyeballs. There are some very strong diagonals, right? So we're going to get some structures. So we have in this interface several things going on at once. So we can just play backwards. We can play all of Michelle. That's great. We also have the ground truth. And I think, actually, do you know right off the top which one's the ground truth? Top or bottom? Can you guess?
Oh, we just looked at it.
Seriously,
I think the bottom is the ground truth.
Okay, so it is now. So the bottom's the ground truth. The music school folks, they did that. That's what the ground truth is. And the next one up is one of the algorithms gave us that. And we could change that. We can select that. Because, there's no real sort of perfect answer to this. So, I don't know. How about that one? So I don't know which one changed. You can probably guess which one changed. Bottom one changed, I guess. Right? So yeah, so that's another version, another kind of analysis. So each one of these sections is selectable. So we can jump to the various sections. And you can hear actually how good this is. So there's the B section. Oh, another B section. Another B section. Cool. Maybe not. And there's C. So, not the computer did this, right? Not a human, the computer did that, right? So that's pretty good, right? So I'm really quite happy about those kind of results. And so the one thing, one sort of groovy little bit that sort of brings all this stuff together, in older MIR research, we tended to treat the song as one single unit. And I always found that problematic because moods change over sections, keys change, structure. I mean, it's the whole point. That's why we have these structures, right? The exposition and modulations, and that's why we have these architectural structures, is to go to different regions of the world, in the musical world. Now we can get into the structural analysis where we have meaningful subsections. Those subsections themselves convey a little package of information. So why not make one of those little packages of information the query for something else? It is that little sub-package that could be the basis of the next query. And so what we've done is for each one of these, we can take the section and submit it as a query to the AudioDB search engine. And it will find all the places where that section has similar results across your entire collection. So it's not the entire song. It's I don't know, was that the Michelle bit or the other bit? I don't know, can't remember. But anyway, so something that's similar to that across your collection. And that, I think, is really important. They're getting more fine-grained about what it is. And I think it's especially more important for mood searching. So you can see where stuff happened here. So we go back to, it should give us where it found it. See, there's the matches. Of course, because you should find it. Right? So that's, we can search across that, and then we get some interesting results here. I have no idea what's. Sorry? Okay, I'll go back to it in a second. So here's the match there. I don't know how close it is. Not the most convincing thing in the world. So where's Ride the Lightning? Okay, this one? Oh, Metallica. Okay.
That's only like 1%.
Yeah. My bell. Yeah, the percentage there is pretty low. It's about 83%. Yeah, then those numbers are a little bit make-believey. I'll tell you that from the, yeah. Okay, so the one thing I do want to show you is, and this is my contribution to science right here. So we have these diagonals, right? And one thing that we want to do is as a researcher, is to see what it is in time. What is the thing that's getting picked up as the equivalence? I mean, why is this a diagonally thing? Well, we invented the diagonal writer, and I'll show you right here. So I'm on. See this little pointer here? Sorry, I can't see. Oh, so little pointer here. Okay, I'm going to place it on the diagonal, and as we know, this diagonal should just reproduce the music as it is. And what we're going to do is for one axis is going to go to the right speaker. The other axis is going to go to the left speaker, so we can hear in time what's matching up and what's not matching up. So I'm just going to play it from there, make sure I nailed it. Yeah. Nothing too exciting there because that's the way it should work. That they're both at the same playing at the same point in time. A little bit off. Right? Cool. Anyone not convinced? Like sort of that's. So what I'm saying right now is that we split the audio. One of the axes is playing from one side, and the other axis is playing from the other side. Okay. So and I'm gonna pick some random junk. I'll pick random junk later. Let's just pick another section. Here's one of these diagonals, though, right? Off diagonals. That's what the computer's picking up on. Kind of groovy, eh? I mean, it'll drive you nuts because they're not perfectly in time. Right. So yeah. So anyway, so that's the thing so you're going to start exploring the strength or what it is that the things are picking up on. So sometimes it alerts to be the chambers. Maybe it's just the chord changes are the same and everything else is different, right? Well, that's the closest thing I've come to my contribution to musicology. Is that tool right there and exploring these data sets. So that's pretty much it, I think, for the demo-y stuff at this point. The one last thing I just want to show you before I give my closing comment is something that this is an older version of the Salami, and what I really want to show you is in this help stuff. So one thing we do get in a lot of trouble over time, there's that slide, the world famous slide, about the stuff, the similarity. Where'd the scores go? Oh, I know where I'm going. Pardon me? It's a comparison I want to go to. So these are the scores for the algorithms, and the one thing I just wanted to show you, this is all generated. This is one of the most interesting slides. So these are the scores for how well each of the algorithms did against ground truth, the ones that were submitted to Murex 2010, if I got it right. So we use a statistical testing thing called. Yeah. So now I'm blanking. I need a beer. So Tukey-Kramer for the honest significant difference. Anyway, we run statistical tests, and basically it turns out that these ones did okay, but they're all the same. So MHRF2, MMD, and WB1, they're all of you can't say one is better than the other, right? Then we have sort of a second group down here, and we have one that didn't do too well because actually we didn't run. There was a malfunction. This one up here is humans. Right? So what we did is, remember, we had 2 humans for each one of these double-keyed ones. So we declared one to be ground truth, just arbitrarily declared one to be ground truth, and then measured how well the other person did against that ground truth. Only 70% agreement between 2 humans doing the exact same task. But that's a very important bit of information. That essentially says, right, that if we can get computers to start getting up to that 70% realm, we're not going to do much better. Right? If we use humans as our notion of what the baseline is, which I think, ground truth is an awful phrase because people get hung up on the notion of this is truth. It's this sort of baseline we need better terminology for it. But if we get these things up in this area, then we're getting the computer to essentially perform like a human in the music domain, which I think would be kind of great. Okay. So, to answer the question, the closing comments here. So is this e-science or is it e-musicology? I'm going to have to say it's still e-science with cool things going on in the musicology realm. What we need is people with musicology backgrounds to help drive more deeply into the music, inspire the music questions more deeply. And then I would just love to participate and help you build these things and swim in this data. There's a lot that... Yeah, and you have to take the lead. The one thing I'd like the e-musicology folks to do is to take the lead because, as I mentioned earlier, as much as I love electrical engineers and computer scientists, they will tell us what they think is best and prescribe, and it'll be kind of half-assed. Right? But it'll be the standard, and it'll be harder. It's harder to dig yourself out from underneath that. So we got to get a little bit more involved in these early days and define projects. I think the whole digging to data challenge is great because it comes from the humanities backgrounds, right? So that's why I liked it a lot, and I like it in the second iteration. Those SHRC programs and other programs that have a strong humanities background, I really applaud. So anyway, right now we're kind of like triple pianissimo to maybe mezzo forte, but not much louder. And that, more or less, is the end of the talk. There's a couple little video demos if you want to click on them in your spare time. You can take a look at them. And this is where I say thank you to everyone. Thank you.